video, we're going to do a quick recap of some of the concepts that you might have learned in your strength of materials class or your mechanics of materials class, otherwise known at Miami at least as MME 312. All right. So for MME 312, we oftentimes talked about idealized or simplified cases, such as if you had a cantilever beam with an applied load, concentrated load P at the end. In reality, that most of the time, there's no such thing as really a concentrated load. You might have more of like a pressure distribution or a distributed load. Oftentimes where we're going to be interested in to determine our stresses are going to be our stresses within systems is we want to find out what is our total force due to a pressure. All right, so to find our total force due to a pressure, we can say that it's going to be equal to the integral of that pressure, which might be a function of, let's say, x and y, times dA. All right, if that pressure, P of xy, is a constant, we can say that it can bring it out, and then we just integrate it over the area. So what we end up getting is we can say that our pressure is going to be equal to the total force divided by the area. Right? So we can use this for simple. So the simplest form of stress we define is going to be equal to pressure, or it's a normal stress. So we can say that our normal stress theta is equal to our normal force F normal divided by our area. All right. Now this can be either positive value if the force is pulling against the body, or it can be negative, which would be compressive. All right, so this would be positive, we'll call it a tensile force, and then negative would be a compressive force or compressive stress. All right, and then the second type of stress that we talked about is when instead of having a normal force, you have a force that's tangent to the area, and this is called a shear stress. All right, and then so shear stresses can be positive and negative as well. However, it's not as critical as normal stresses to know if they're positive or negative. It doesn't affect the failure criteria in the same way. Anyhow, that's getting ahead of ourselves here. But two of the most common cases are where you encounter shear in common engineering components are if you have a pin that connects two bodies together, like we have on the left-hand side here, all right, at this surface in the middle here of the pin. What ends up happening is our pin has a force that's being applied by one bar and has another force being applied by the other bar, and we can say that the shear due to this force is going to be equal to tau O is going to be equal to F over A. While in the case of if we modify our pin connection to include a U bracket that connects to a joint, what we actually end up having is we have two surfaces in contact. So what we end up getting is if we highlight this section here, is that we have one force P over 2, another force P over 2, and another force P. So at the worst case scenario, the largest internal force is going to be equal to P over 2. So we can say that the shear stress is going to be equal to F over 2 over A, or it's going to be F over 2A. Okay, so these are some common cases where you have a uniform stress throughout a body, and these are the formulas that you're expected to know for calculating those uniform stresses. And that concludes this video on uniform stresses. Hopefully this was nothing too new for you compared to, you probably covered this all in your strength and materials class.